Okay, so I want to thank here the organizers to give us the opportunity to present our work on lithophobic heterogeneous systems and the possibility of this system to be used for energy dissipation application and maybe tsunami energy dissipation. So this work is done in collaboration with Gérard Vigier, who is at Laboratoire Mathéis INSA de Lyon, and Ludivine Guillemot and Milan Michelin-Jamois are our previous and present PhD students. So lithophobic heterogeneous system is composed of two ingredients. One is water, and the other one is a porous medium, which is hydrophobic and has pores in the range of the nanometer. So such porous media are nowadays available with very well-defined pore sizes and tunable pore sizes, thanks to the progress of solid-state chemistry. And the medium has to be hydrophobic, which means that creating a contact area between the water and the pore involves a high energy cost. So the idea of hydrophobicity is sketched here with a drop which is resting on a flat surface. And you see that the drop has a round shape because it wants to minimize its contact area with the hydrophobic plane. So the idea here is to force water to fill the pores of the nanoporous medium. And this involves high energy because there is a lot of contact area with the water and the pore wall. So for doing this, one has to apply a pressure on the liquid. And actually, the pressure volume curve is a characteristic of the system. So basically, when pressure is applied on the liquid, the water starts to enter inside the pores at threshold pressure. And if the pore size is well defined, then the intrusion occurs on the pressure plateau here, which we call the intrusion pressure. And when this plateau is finished, then the pores are completely saturated with the water. So doing this, one transforms mechanical energy into surface energy, and the amount of energy involved is the area under the pressure volume curve. When the pressure is released, one can have different behavior which corresponds to different energy application. For instance, the liquid may go out of the pores at an extrusion pressure which is not very different from the intrusion pressure. In this case, one recovers the mechanical energy and one has a system suitable for energy storage. Or the liquid may empty the pores at an extrusion pressure which is lower than the intrusion pressure. In this case, one recovers only one part of the mechanical energy, and the energy dissipated is the energy inside the hysteresis cycle here, and one has a system suitable for vibration damping. And finally, the liquids may not go out of the pore at the atmospheric pressure, and in this case, one has a one-shot energy dissipation. So the amount of energy involved in this transformation is the product of the area of the internal surface of the pore walls times the strength of hydrophobicity. The latter is the energy difference between the wetted surface and the dry surface. So the strength of hydrophobicity can also be measured in terms of the contact angle that a drop makes on a flat surface, which is equivalent to the internal pore wall surface. So reasonably high hydrophobicity, actually quite high hydrophobicity, correspond in practice to a contact angle of the order of 120 degrees. It's difficult to obtain a larger hydrophobicity. And in order to get high energy, one also needs a porous medium with a high specific area, which means a high pore wall surface inside the material. So current specific areas are in the range of 200 to 1,000 square meters per gram of material. And putting all this together, it gives energy of 100 kilojoules per kilogram of stored water. So I want to emphasize that this is a reasonable energy concentration. It corresponds to a gravitational energy of 10,000 meters. So it means water raised above the altitude of Mount Everest. Also, a high specific area corresponds to a small pore size. And this means that the intrusion pressure is quite high. Actually, in a cylindrical pore, the intrusion pressure obeys or should obey the classical law of capillarity and grow as the inverse of the pore size. And this corresponds to typical intrusion pressure in the range of 20 to 100 megapascal. So 200 to 1,000 bars. Okay, so we have studied the behavior of lyophobic heterogeneous systems using a specifically designed high-pressure cell and traction compression machine. And we have studied model porous media, which are micelle templated silicas made hydrophobic by silane grafting. And the porous volume of this porous material is made of cylindrical pores which are not connected between each others and which have a small dispersion in the pore size, so a well-defined radius. Okay. So what we found on this well-defined porous media is that the intrusion pressure indeed follows the law of classical capillarity and grows with the inverse of the pore size in a linear way with a contact angle of about 120 degrees for our silane grafting treatment. So this means that this quantitative law allows one to design porous material able to meet well-defined intrusion pressure by tuning the pore size of the material. Now, the extrusion pressure does not vary with the same law. This is the log-log plot, and the 1/r power law is above for the intrusion pressure. And you see here that the extrusion pressure varies much more quickly with the pore radius. Actually, this is why one can have hysteresis cycle in the materials. And for large pore size, larger than 4 nanometer, one doesn't have any more extrusion at the atmospheric pressure. So the reason why the extrusion pressure doesn't follow the same law as the intrusion pressure is because in order for the liquid to go out of the pores, the liquid has to somehow to form two disconnected meniscus which can then empty the pore. And of course, this costs some extra energy. So this energy barrier can be actually calculated by considering a bubble which is growing on the pore wall. And the maximum energy of this bubble corresponds to critical energy to be overcome in the extrusion process. And this energy can indeed be calculated and expressed analytically as a function of the pore radius and the pore hydrophobicity. So in a nucleation picture, this extra energy is provided by the thermal fluctuations, so that the nucleation rate is determined by a Boltzmann factor. And one obtains the extrusion when one waits long enough to obtain one critical nucleus in each pore and a breakage event in each pore. So this gives us an expression for the extrusion pressure, which varies quite heavily with the pore size, because it depends on the volume of the nucleus, which of course varies as the third power of the pore size. So we have been able to study the variation of the extrusion pressure with the function of velocity, and we have found that it corresponds very well to this nucleation picture. So the points here are the experiments, and the lines are the nucleation model. And we see that the pressure has a logarithmic variation with the extrusion time, which means that it depends very weakly on the velocity. So on 3 order of magnitude of the velocity, the pressure varies only by less than 10%. And the intrusion pressure varies, it's almost not possible to tell how it varies with velocity, because the variation is very small. With the temperature also, we have a behavior which corresponds well to the nucleation model. And the result is that the extrusion pressure varies also a little bit, but not very much, with the temperature in the range of ambient temperatures. And so the conclusion is that we can reasonably tailor hydrophobic porous materials so as to achieve definite values for intrusion and extrusion pressure, and then therefore to meet various requirements for energy dissipation or storage applications. And also these characteristics vary quite little with parameters like velocity or frequency or temperature. So how could we use those materials for tsunami energy dissipation? So we want to use pressure volume cycle and dissipate energy with this process, and we could think of damping pillars, which would be hollow structures hosting the liquid and the powder, and equipped with pistons, and on all their height. And these pillars should be equipped so as to concentrate the force exerted by the tsunami wave, so as to obtain high pressure at which the dissipation will occur. So this could be maybe by forming pillar line, by relating the pillars with some reinforced textile, or by using forests of individual pillars, which would be equipped with a forehead front here in order to concentrate the tsunami force. So we can make a very rough estimate for tsunami dissipation power by considering a wave 20 meter in height, 10 meter in thickness, that would be the peak of the wave, and a propagation velocity of 10 meter per second. And we could consider the incoming energy in terms of the kinetic energy and the potential energy of this wave. And then we could balance a wave with the length of L along the coast, and the energy absorbed by one pillar, which of course depends on the intrusion pressure and the volume inside the pillar. And we find that using the high intruding pressure, the pillar can absorb all the tsunami wave if we have a pillar array separated by 10 meters and with internal volume of 30 centimeter in thickness and 2 meter in length. And what else should I say? Maybe that the pressure on the forehead plateau here is 3 megapascal. And here the calculation is made with a high intrusion pressure of 1000 bar. And for this high pressure, the extrusion pressure is not 0, it's quite high. So this means that the tsunami will be sent back to the sea. Well, and of course, this is a very rough calculation, and it does not include any hydrodynamic calculation on how the wave behaves while it is damped into this structure. Okay, thank you for your attention.